Hi, this is Nalini Elkins with Industry Network Technology Council. If somebody can send me a quick note to let me know that you can hear me okay, that would be wonderful. If you have any problems with the audio or video, please let me know. And as always, we are recording this webinar. Yes, I'm getting some notes that the sound is fine. Good. Yeah, just let me know if anything happens. And what we will be doing is I will start off the presentation, and then I will have the students and Priyanka talk on what's going on. And as I say, you will get all the slides after we are done. Let's go ahead and get started. So this is a project that we have with it's a collaboration between INTC, a nonprofit in the United States, as well as IISOC, a nonprofit in India. And you will see one of the results of this collaboration here today, a sample collaboration with what we are doing. We want to promote IPv6 deployment at enterprises. It has unfortunately lagged, and that is due to, in some ways, I will say, the complexity of IPv6. And so that's what we want to clarify for you on these. If you have any ideas for future webinars, do please send me a note and let me know. We are glad to do that. Just a couple of words about me. I think many of you may know me. I have been in the industry for quite a while. I'm the president of the Industry Network Technology Council. And this particular webinar is a collaboration not just with IISOC and INTC, but NITK Surathkal, the National Institute of Karnataka at Surathkal is one of the national universities in India. I believe it is ranked number 10. So we are very happy to be working with them. We have a memorandum of understanding with them, and they are a very valued partner. And in particular, Dr. Mohit Kalyani, he has been the faculty advisor that has worked with us to provide students to do various projects with us. And let me just, as an aside, let me say that if any of you would like to participate, if you are at a university and you would like to have your students or faculty participate with us, we are very happy to add you to some of our groups. We have lots of projects that we want to do. So do let us know if you want to work with us. Today, what we're going to talk about is Neighbour Discovery and the enhancements that the students have been working on for Neighbour Discovery. So let me first give you a refresher on what Neighbour Discovery is and why we might need some enhancements for enterprise networks. So I'm sure you guys are all familiar with ARP in IPv4. So Neighbour Discovery not just replaces ARP, but adds quite a few other substantial improvements to it for IPv6. You will see some of the major messages in there: router advertisement, router solicitation, neighbor advertisement, and neighbor solicitation that are used for basically getting your address and figuring out where to route, in one part, where to route. But in essence, the basic idea is to get the address. It's of course far more complex than that. And we do have two different presentations that really talk about what neighbor discovery is, and a lab to show you. So if you wish, you may go back to our INTC or IIESOC webinars and review those. So let me tell you some of the problems with this, though. If you have a very large subnet, for example, at enterprises, sometimes people want to put the entire wireless into one LAN, or you may have a VLAN that is a very large, subnet. What can happen in there is that some of these messages, for example, duplicate address detection, which goes out as a multicast to everyone on the group, really ends up being a broadcast message to everyone. And it's really duplicate address detection should be a unicast message. That is, it's only really intended for one device, but it's going out as a multicast to all nodes, which makes it a broadcast. And if you have many devices joining, getting off, joining, getting off, such as can happen with Wi-Fi, this can create a great deal of traffic. And so this is the problem that we are trying to address in this project, is what happens at that point then to the packet flow and the cache that is in your devices, the neighbor cache, which is in each device, and also maybe at the switches and so on. So what we've done is, with the help of Dr. Pascal Toubert from Cisco, who wrote a number of the RFCs to reduce this kind of stuff in the IoT world. These are RFCs for 6LoWPAN and roll, that whole area. We integrated those into classic neighbor discovery. So that is to set the stage for what the students guided by Priyanka will tell you about. So we have Dr. Priyanka Sinha, who has guided the students, and then we have 3 students who have been working on this project from NITK. They started out, Sudesh started out as an undergraduate. He has since graduated, but he still is kind enough to work on the project. And then we have Kavya and Advait, who are both undergraduates, I believe in their senior year now at NITK. So without any further ado, let me turn this over to Priyanka and the students. And so let me, Priyanka, I'm going to go ahead and unmute all the students so you can speak. And so you will have to unmute yourself and go ahead and start up whenever you're ready.
Thank you, Nalini, for kindly setting the stage. I am Dr. Priyanka Sinha. I am a board member at the India Internet Engineering Society, IIESOC, and a member of the INTC, the Industry Network Technology Council. I'd like to reiterate and repeat what Nalini has just said, that through this project implementation, in enhancing neighbor discovery for IPv6, our goal is to reduce the chattiness in the operations of the IPv6 protocol. Right now, neighbor discovery uses a lot of multicast, which often becomes a broadcast periodically. On the team, we have Kavya and Advait, who are final year undergraduate students who have been volunteering on this for more than a year now. And we have Sudesh, who was a student of NITK, has been leading the effort from the start and is now working full time at Oracle. This project was motivated by Pascal Thubert's talk here last year, where the wireless 6LoWPAN enhancements that we see in RFC 8505 and 6775, we see that there are viable mechanisms for reducing the chatter in enterprise networks as well, and in some way reducing power consumption, even with slightly larger packet sizes. For the immediate, we are attempting support of the RFC 8505 EARO address registration option for neighbor discovery. So we have Sudesh upcoming walk us through their efforts with Free Router, which is an open source router implementation, and the Linux client. Over to you, Sudesh.
Yeah, thanks, Priyanka. Am I audible? Can someone please uh,
Yes, yes,
confirm that?
yes.
Yeah,
Uh,
thank you. Thanks,
in-
Nalin.
Yes, please let me know which slide you want me to go to.
Yeah, the hypothesis part, please.
Okay, all right.
Uh,
So,
the next
mhm.
slide. Yeah, thank you, thank you. Yeah, hello everyone. I'm Sudesh. As introduced earlier, I was a student of NITK, now a graduate. So yeah, let's begin with what the hypothesis of this project is. So as said earlier, the neighbor discovery, classic neighbor discovery IPv6 ND will refer to whatever is in 4861 RFC. We'll refer to it as classic IPv6 neighbor discovery. So it is very chatty since it is communicating all the neighbor solicitation and advertisements through the multicast messages. But now RFC 6775, which is meant for, which is called the 6LoWPAN neighbor discovery, is focused on low power devices, which basically tries to reduce the number of messages and thereby reducing the chattiness of the classic IPv6 ND. So the number of ND messages, which is neighbor discovery messages, will be reduced. In particular, neighbor solicitation messages. Neighbor solicitation, we in our 6LoWPAN ND, we will be using neighbor solicitation messages as a part of the mechanism to register the addresses in the neighbor cache of the router so that it can be accessible. So yeah, thereby reducing the number of messages will thereby reduce power consumption as well. And now uh, also ND messages go periodically, and these are mostly unicast. Neighbor solicitation and DAD are converted to unicast, whereas in classic IPv6 ND, which will be multicast. So yeah, and with our approach, NS will increase in size slightly because we are adding a few options to the ICMPv6 packets, uh, which are like which will be introduced in further slides. Can you change the slide, Nalin? Yeah, next slide, please. Yeah, so the modifications that is proposed in RFC 6775 and 8505 are, first thing is to, as said, optimizing neighbor discovery by avoiding multicast splitting as stated earlier. And one important thing is here host initiated interaction. So what would happen is in a classic setup, a router will start advertising its address saying that I am at this address and whatever address is there. So that would happen periodically, and this would also lead in increase in the number of packets. And this is not very suitable for a low power case, and it increases chattiness as well. So what is being done in case of RFC6 as proposed in RFC6775 is host will send a neighbor solicitation message, or it will initiate the interaction where it should register the address, and thereby it will get a reply in that way. So it is host initiated, uh, to say. And host address registration, yeah, there is a new mechanism introduced which is basically host address registration using an option called as ARO, which is address registration option, which will be sent in unicast neighbor solicitation and neighbor advertisement messages. So how it will be used in neighbor solicitation and neighbor advertisement messages is, so in neighbor solicitation, whenever a host comes up, it will send a neighbor solicitation message saying that I am in this address. So and router will use this information from address registry ARO option to create an entry in the neighbor cache uh, with that host address, IP address, and MAC address to register it in the neighbor cache. And it will also set a registration lifetime which is specified in this address registration option. And also there is a field in this option called as EUI64 unique identifier, which is used to which is basically unique, assumed to be unique throughout the network, so that in order to avoid the uh, duplicate addresses or any other case to uniquely identify each host basically. So that is there, and registration lifetime is there. So these neighbor cache entries will have we can this allows us to set a expiry time for neighbor registrations basically, after which we'll have to re-register the address again by sending one more neighbor substation message from host side. That is how it's there. And router will register this address and send a neighbor advertisement in response to the host. uh, and to repeat again, all of these will happen in unicast. So there won't be multicast flooding, where the router will send it over across multicast address saying that all of you just read this. No, it happens across unicast. So which is the whole point of this. And yeah, it will send a neighbor advertisement to the host directly, and with a status flag set which says whether the address got successfully registered or not. uh, that is the basic mechanism of RFC 6775. And there is authoritative border registration option, which is like there will be a border router which is placed across route, which is connected to all the routers, which will basically contain the global information of how the whole what are the hosts being registered. And basically it is used in our case to detect duplicate addresses in a global space. If it is linked local, we need not worry about the duplicates at address detection according to our topology. But if it is global, we need to check for duplicate address detection if you're registering a global address. In that case, this AVRO is useful, where we'll register this saying that this is our border router. And yeah, it is basically useful in that case. Can you go to the next slide, please? Oh, Nalini, can you change the slide to next one?
Yes, next one still.
Yeah, here. No, 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 the previous one. Sorry, RFC 8505. Yeah, yeah. Thank you. This RFC 8505 is a proposal of extensions on top of RFC 6775. So it basically tries to generalize the mechanism which is already proposed. So new option is introduced, basically extension of address registration option is introduced, which allows us to register on behalf of other nodes. Basically another proxy kind of, there is this neighbor discovery proxy concept, which can register uh, a different host or node on if it can register on behalf of that node to a registrar, whoever is registering these addresses basically. So yeah, that is one thing. And it also tries to generalize the EUI64 part. EUI64 identifier was based on MAC addresses, but this tries to generalize it and gives cryptographic extensions. I can use some secure ND related things here and use the ROVR. We'll go to the packet format address option format in the next slide, but yeah, it allows us to specify this uniqueness through different option format, different ROVR formats basically. Yeah, as you can see, this is the ERO option format. ERO option is also very similar except for a few fields changed here and there, which I'll uh, tell about in just a minute. So type code is 33, which is specified, and length will specify the length of the option in multiple of 8 bytes. And then status is used by the used by the router to tell whether the address registration was successful. and opaque and IRT are basically used, but yeah, those are used in terms of 6 low power in the context of 6 low power devices, which will a kind of skip for now. You can refer to RFC 8505 for further information on that. And there is one more thing introduced here, which is the T bit, which you can see, and the transaction ID, which helps us to identify whether this is a re-registration. So the concept is this node can move in between routers, and it should still be able to register with the border router, which is like sitting on top of these routers. So it should be able to register multiple times and still be able to detect whether it's re-registration or a duplicate registration. That's the whole concept behind transaction ID, which is TID. And then there is registration lifetime, which is specifies the validity time for this registration, whatever host is registering, or the host should make sure it re-registers this after the immediately after the expiry of the neighbor cache entry. And then there is ROVR, registration ownership verifier, which extends on top of the US65 format in AR option, which is variable in length again. It has support for 5, 6, 7 multiples of 8 bytes, which can be used also, which gives more flexibility in terms of the identifier as such. So this was about ERO option format. Now going to the registration flow, this is some of the part can be ignored for now since it's not implemented, but the main concept is there is 6LN, which is 6-LoWPAN node, 6LR, which is 6-LoWPAN router, 6LBR, which is 6-LoWPAN border router, and routing registrar, which will basically do the store the registrations which we are doing. So 6-LoWPAN will be on link local to the 6-LoWPAN router, which will send the neighbor solicitation. As said earlier, this is a host initiated interaction, so it will send neighbor solicitation with EARO option. And yeah, these DAR I didn't mention, but there is duplicate address detection which is happening over this network, which will happen through these special messages, special options called as special messages to say, which are DAR and DAC, which is duplicate address request and duplicate address confirmation, which basically does duplicate address detection through the help of 6 LBR, which will contain information from all the 6 LoWPAN routers, a centralized kind of thing. And then 6 LBR will act as a proxy. As I said earlier, 68505 allows the registration on behalf of other nodes. It is registering the 6 LoWPAN node on behalf it's registering the 6-LoWPAN node through 6 LBR, and it is acting as a proxy, and it is registering to the registrar. We can do it directly also, but this is a generalized scenario which is being generalized example which is given in the this thing. And the proxy will send neighbor advertisement with ERO with the status codes to say whether. Also, the one more improvement enhancement in terms of status code is it gives more it introduces more status codes, so that it introduces more status codes in ER, or like the about the registration itself, to enhance the debugging, so that a neighbor 6-LoWPAN node can take more decisions whether to re-register it or do anything with that. You can refer to RFC for that information. And yeah, it registers and maintains the route proxy state and whatnot. Registrar will register it, and neighbor advertisement will come in with a status finally. So this was the registration flow of the whole 6-LoWPAN registration. Yeah, this was about the uh, modifications that these RFCs 67775 and 8505 suggest us to reduce the chattiness of classic ND, and enhancements on top of it to make it more reliable and yeah, secure to say. Yeah. Can you go to the next slide, please? Yeah, now coming to the implementation part, what we are choosing to implement these specific RFCs is one, on the host side of modifications, we are doing it on Linux kernel. We are putting efforts on that side as well. And one more effort is on the free router side. free route. Yeah, I'll speak about free router, free RTR now. So free RTR is a free and open source control plane software, which is basically a router software, which is implemented in Java and has immense protocol portfolio. It supports a wide range of protocols that we can use, and it can interact with very like huge, wide variety of data planes. So that is one advantage of it, and it is actually from the free router website we get, it says that it's one image for all protocols you'll ever need in routing. In that way, we are doing modifications in this source code to integrate the ERO support, RFC 677 and 8505 support, and it's currently being used and developed at RARE, which is Router for Academia Research and Education RARE project. And this is not uh, running on the kernel stack. It kind of runs as an application and operates on socket, not on physical interfaces that are there, or virtual interfaces that are there on the Linux kernel. So it is system independent in a way. I can run it in any system, and yeah, I can run it as application. Easy to compile, do do modifications and attach to it and do stuff. So this is one choice. This is one reason for choosing this, and it relies on UDP sockets. It communicates through UDP sockets. So we are binding it. Yeah. Can you go to the next slide, please? This was a brief intro to FreeRTR. Now, yeah, we are different test beds we are trying to focus on is a free router on network namespaces, free router on Raspberry Pi to get a physical sense of how things work. We'll introduce water names, network namespaces in a while, and we are trying to do it on cloud to get a notion of uh, without link local how it works and stuff. And further, we are thinking of testing it on actual routers as well. Next slide, please. Yeah. So network namespaces are basically like isolated groups, isolated inside the one. I can basically run different network topologies inside my host machine itself. I am emulating in a way. I'm not simulating here. I'm emulating by creating a network namespaces which have their own Linux kernel network stack, which have a duplicate network stack. So I can easily interact, and the setup is easily done inside a network namespace without having to, without having different number of machines itself to test my things. So it encapsulates the network interfaces and route tables, etc., which are there, and these source resources are basically isolated, and I can make them communicate with each other. So I can try out different configs, like I can set up different firewall rules in each of these namespaces. Basically, if I have a host router, border router, whatever, I can just emulate the whole topology inside my machine and test it out. That's the which are independent of the underlying host OS. I mean, I can set have a different firewall rule or routing table in my OS and have different firewall in each of these namespaces. So I can test out my network experiments on these network namespaces very easily. That's about network namespaces. Can you go to the next slide, please? Yeah. So now, how are we doing this free router setup on network namespaces? Uh, so the issue, one hurdle we had to pass while using free router with network namespaces was that free router works on socket level as mentioned earlier, and these interact with each other well. If I do have two routers, free routers, I can communicate, I can set up topologies there well. But we are doing the host side of modifications on Linux kernel and router modifications on free router. we need we needed a way to interact with each other. Yeah, these are router and host are basically network namespaces that we have created, or we can consider them as different Raspberry Pis that we have, or different uh, machines that we have where we are basically running these tests. Router width and host width are basically the interfaces through which we are communicating between these two devices, and free router is running in the router. So there is a interface socket which is running through a socket, which is not actually an interface. It's kind of a simulation from, yeah, uh, it is kind of an interface which we have to bind to from the namespace, which we are doing through some utilities provided by free router itself. We are doing it in that way, and we are communicating. We are able to establish communication between router and host and seamlessly be able to communicate, thinking that this is actual router and this host, and we are able to do experiments on that easily. Yeah, this was about the whole setup on of free router on different devices. Can you go to the next slide, please? Yeah. Now, how have we implemented RFC 8505 in free router? So, our free router didn't have support for SLLO, TLLO, or ERO options, which are introduced in these RFCs 6775, 8505. So we needed to parse these options. We have modified change, we have made changes in the code to perform these changes using different uh, techniques of parsing the packet, parsing the ICMP v6 options. These are basically ICMP v6 options, right? So we are parsing these options separately, SLLAO, TLLAO, and parsing different fields in this, which are mentioned like SLLAO will have the source MAC address, or TLLAO will have the target MAC address, which is to be registered. ERO will suggest that this is to be registered with this registration lifetime, and I am the one registering the unique identifier stuff basically. So we are passing all those, and yeah, and after parsing these, we are performing neighbor registration and storing it in neighbors router's neighbor cache. So performing neighbor registration, even the neighbor cache has to be modified because it has to support new fields like ROVR and registration lifetime uh, to to set the expiry of that specific neighbor cache entry. So we are doing that right now, and we are able to update the neighbor cache accordingly and perform neighbor registration and neighbor cache entry expiry set. And we are after the neighbor cache entry is uh, expired, we are not basically considering it as an entry, and we'll purge it whenever required. And all those logic is implemented as of now. This is based on the as mentioned earlier, it is from the registration lifetime field in ER option, which is mentioned in RFC 8505. So we have made these modifications in RFC 850 in a free router to support these as of now, and it's kind of work in progress that we are doing. Yeah, can you go to the next slide, please? Yeah, about the host side of modifications, the Linux kernel modifications are also in progress, and it's kind of right now we need a mechanism to just test out the router side without having the host ready, because all both of these developments are going in parallel. So we chose to create a packet ourselves rather than uh, we chose to create a packet ourselves rather than waiting for the Linux kernel modifications, which generates packets and send it send it to the router. So we create a kind of crafted a packet in Scapy which supports this option. As you can see, we have added a support for new option called as ERO, and you can see that type, length, status, TID, registration lifetime, all of these are being populated, and we are crafting the neighbor solicitation, neighbor advertisement packets, and directly sending it to the router, free router, so that it can be parsed and it does the registration for the time being. So that is how we are testing out this. So yeah, uh, that was about the crafting of packet and testing out. Now let's go to the actual. Can you go to the next slide, please? Yeah. So yeah, neighbor table entries. Yeah, how we are testing it is basically as seen in the topology earlier. We have two namespaces that are set up. One is host, one is router. Host is basically Linux kernel where we are running this KP program to send over the packet, uh, which has all these options like SLLO, TLLO, and DRO, which can help in performing the registration on the router end. uh, we are crafting that packet and sending it across the namespaces which we have created, where we have created a link and with pair which can actually send the packet over. So that we are doing on the host side as of now. On the router side, as I said, free router runs on socket level. UDP natively relies on UDP sockets, and we need to bind it to the interface so that it can easily interact with the Linux kernel. So free router has provided some utilities to do this. The initial purpose of which was to basically do a packet capture on these free router sockets, but we are using it to send the packets itself, so which works in the same way. So we are doing that, and we are disabling the, if you had seen, the router had a router width which was actually the interface, but the disadvantage of this setup is that even the router width will start sending neighbor solicitation, neighbor advertisement packets, or router solicitation or router advertisement packets, which are undesired in this case, because we just want the free router to handle all the IPv6 neighbor discovery or whole IPv6 part, because this is the software that which will run all our logic. So we have disabled, there is, we can disable IPv6 in Linux kernel by writing it to a file which you can look up. Basically, we are setting an option in the Linux kernel which we can run a command and it writes to that file and it will disable IPv6 on that specific interface. We are doing that to disable IPv6 from the Linux kernel perspective, and we are allowing, by thereby allowing free router to do all the neighbor solicitation, neighbor advertisement, and all of these things. And we compile the free router uh, Java binary to have all these changes that we have done, and we are enabling some debugging on our end to do that. So if you can see, these are screenshots from the basically it's displaying the neighbor cache entries. If we when initially if we see if we do show IPv6 neighbor eth1 is the name of the interface that we have given in the router, which was kind of default given in example for free router which we are kind of using it right now. We can see that the neighbor cache is empty, and after we sent a crafted ERO packet, as I said earlier, we are crafting from Scapy for the time being until the Linux kernel implementations are changed. Linux kernel implementations are being done parallelly on the side uh, to the router from host to see if router is able to register the host node. And we can see that the MAC address which we had given and the IP address, and we can see how much time it has elapsed and what is the registration lifetime, and static and router like already supported entries in the neighbor cache. We can see that the address is getting registered through the AR option on sending a neighbor solicitation itself. So thereby demonstrating our work till this point, that saying that, and it will, this will expire after we wait for 65,000 milliseconds, which will basically be 65 seconds. So in this case, this is the work that we have done till now. And yeah, can you go to the next slide, please? Yeah, now the future work that is to be done is, as we saw, there is transaction ID being used. We have still haven't implemented the logic for border router and transaction ID, which happens. We are just having a simple topology for testing out our changes to implement 6775 and 8505. We still need to develop support for uh, 6-lopan border router which will contain information of all these, and we need to kind of do duplicate address detection. As you saw earlier, we need to still do duplicate address request, duplicate address confirmation from 6LBR, which is 6-loop border router, and then use transaction ID to add a layer on top of the duplicate address detection so that the node can easily move in between routers. That is there. And as I said, border router logic implementation, and ABRO, which is authoritative border registration option, which is to be implemented on the router side. And we are testing right now extensively on the network namespaces as of now because it is easier and faster to do. We have tested the free router setup on uh, an RPI setup, which where we had physical RPIs connected through a Ethernet cable, and we were doing changes there. And we have tested the RPI side of changes to a primitive level. We still need to do extensive changes after we complete the implementation of RFC 8505, at least the basic implementations, and we'll try to enhance that in future, which is ongoing right now. And we still need to do it on real router and real with huge number of nodes, where we can actually see the metrics of how much the chattiness is reduced by, which all we need to still test. That's there. And Linux kernel changes are, as I said, Linux kernel changes are going on from Priyanka's side with efforts of Priyanka. And Linux kernel changes to be done are still neighbor advertisement parsing and neighbor advertisement support is still to be done on that side as well. Right now we are basically have support for neighbor solicitation at this point in Linux kernel. Yeah, this was about our future work that is to be done. Yeah. Can you go to the next slide, please? Yeah. Uh, this was the huge kind of overview of what we have done till now and what changes we are trying to make to basically improve the basically implement the improvements proposed in RFC 6775 and 8505 through this address registration and whatnot. So yeah, we are open for questions now.
Thank you all so. Yes, this was a great collaboration with all of you students, and then of course Dr. Priyanka Sinha, who has been guiding the students. So it's a great collaboration. And let me give a shout out to Kavya as well. Kavya is one of the other students who has been very involved in it, and very involved in especially some of the hard debugging problems she has been able to find. So let me encourage any of you who are at universities on this call, if you want to collaborate with us, we're happy to work with you, because as you can see, we need a next generation of diagnosticians and architects and so on, who understand IPv6. And there's no better way than working on something like this and really understanding. You can see from what these students as undergraduates have understood how much they're able to do and how much they're able to contribute. And so, as I say, we're happy to work with you. And it's those of you who have actual organizations, or networks. If you want to work with us on various of the other things, as the student says, what we're doing now is modifications to the Linux kernel, and that's a lot of fun. You have to recompile the kernel code and get these things, get FreeRouter talking to the modified kernel. And then we need to do some benchmarking. We only think that this will reduce chattiness, and it makes sense that it will, but we have to do the benchmarking to make sure. And so there's a lot of work still left to be done. And if any of you would like to participate in any of that, just do go ahead and send me an email. We're happy to work with you. And as I say, I think in particular, this will be of use for enterprises on wireless networks. And so we will see if we can present this both at the IETF and at IEPG in the upcoming Prague, just to let them know some of the things that we're working on, even though this project will go on probably for another 1-2 years and involve more students too. So, yeah, any questions from anyone? Otherwise, let me think for a minute. Yeah, so yeah, there's lots of things that need to be done with privacy addressing and so on. But then I think the benchmarking. So yeah, I'm not hearing questions from you guys. Let me check the window real quick, the questions window. And no, I'm not seeing any. Yes, and so do please let me know if you guys have questions after this. Otherwise, let me thank Priyanka and the students for doing such an excellent job on this project. And we will talk to all of you next at the next webinar. Thank you so much.